Hello, I'm back. Okay, these are going to be some alternate examples that I'm going to go through here. And here is the first one, some examples from the video that we just looked at here, some specific ones. Okay, so here's the typical potato chip manufacturer, okay, and buys potatoes from two different suppliers, Riderwood Farms and Camberley Incorporated. The weights of potatoes from Riderwood Farms, as it happens, are approximately normally distributed with a mean of 175 grams and a standard deviation of 25 grams. The weights of potatoes from Camberley are approximately normally distributed with a mean of 180 and a standard deviation of 30. When shipments arrive at the factory, inspectors randomly select a sample of 20 potatoes from each shipment and weigh them, and let X Camberley, or X sub C minus X sub F, be the difference in the sample mean weight of potatoes from the two suppliers. Now, so the first question is, what's the shape of this sampling distribution? So imagine, again, like in the PowerPoint, what we're doing is we're taking many, pairs of samples. One from Camberley, one from Riderwood, right? And we are subtracting them, each pair of samples, to find the mean difference of each pair of samples. We do that for many pairs of samples. And that gives us our sampling distribution of difference of sample sizes, sample weights, okay? Okay, so what is the shape? So we can say A, that the sampling distribution of the difference is going to be approximately normally distributed. And why is that? Because the populations of the two individual potato weights are normally distributed. Okay? B, what's the difference between them? Okay, well, this is X bar Camberley minus X bar Riderwood Farms, so that's where the F comes from. So that's equal to 180 for Camberley and 175 for Riderwood Farms. I'm hesitating here to make sure I get them in the right order. So that's 5 grams. And that's equal to X bar Camberley minus X bar Riderwood Farms. Notice we get one single number. That's the average, our sample difference, right? C, what is the standard deviation? Well, since we happen to know that the two populations are normally distributed, we're free to go ahead and use that sampling distribution thing that we did before. Okay, so this is going to be sigma, okay? Okay, so this is going to be the standard deviation of the sampling distribution is going to be sigma square root of 30 squared, that's Camberley, over a sample size of 20 plus, and for Riderwood Farms it says it's 25, so that's 25 squared. They're both sample size 20, right? And then that would be sigma X bar, or sigma Riderwood minus, or Camberley, minus Riderwood Farms, right? And that turns out to be 8.73 grams, just about. You should try that yourself, okay? All right, so that's first example. So that's kind of like the introductory work, okay? So now, put that aside. Here's another one here. And again, okay, oh look, there's the answers up there, fair and square, in book form. Okay, here's another example. We'll slide this up a little bit. That'll be on the printed notes if you want to look at it, but that's just what I just wrote down. Okay, chocolate chips. Now this is actually an activity they wanted to do in class, but, oh well. Ashton and Olivia wanted to know if generic chocolate chip cookies have as many chocolate chip chips as name brand chocolate chip cookies on average. That is, like the name brand, generic meaning whatever the local supermarket brand is. Okay, to investigate, they randomly selected 10 bags of Chips Ahoy, that's the name brand, and 10 bags of Great Value cookies, that's the generic supermarket brand for whatever supermarket they were in, and randomly selected one cookie from each bag. Then they carefully broke apart each cookie and counted the number of chocolate chips in each, and here are their results. So these are for the sample data for a sample of 10 from sample of 10 Chips Ahoy bags and a sample of 10 Great Value bags. Okay? The problem is this. We're going to construct and interpret a 99% confidence interval for the difference in the mean number of chocolate chips in Chips Ahoy and Great Value cookies. And does your interval provide convincing evidence that there's a difference in the mean number of chocolate chips? Now what we'll do is, we're just going to go straight to the printed solution here. So this isn't super long. Here it is. State. Okay, remember it's the four-step method. We want to estimate mu Chips Ahoy minus mu Great Value at the 99% confidence interval, where mu CA is the true mean number of chips and chocolate chips in Chips Ahoy, and mu GV is the true mean number of chocolate chips in the generic brand Great Value. If the conditions are met, we will calculate, and remember, we've got to write down the name of the test. In this case, it's a 2-sample t interval. Now, why are we doing a 2-sample t interval? Why not a z interval? Well, number one, we don't know anything about this standard deviation of the population of numbers of chocolate chips, and the sample size is small. For both of them, it was 10 bags, right? Rather than 30 or more, which is what we would need to be able to assume normality of this for the sampling distribution. So anyway, so we checked the conditions 3. The random, well, the data come from independent random samples from the two populations, right? And then to 10% conditions, there are more than 10 times 10 or 100 Chips Ahoy cookies in the entire world, and more than 10 times 10 equal 100 Great Value cookies in the entire world, right? So, normal large sample. Now, we had to do this when we did inference for t procedures before, for means, okay? We had to make a little plot. If we didn't know, if the sample size was small and we didn't know the populations are normal, we still have to have some idea that the populations that the sampling distributions are approximately normally distributed. And the way we can know that, the way we can assume that, is getting some idea that the populations themselves are approximately normal. So we made little plots of the sample data. And this would come from the calculator, right? We made little box and whisker plots of the 10 Chips Ahoy cookies and little box and whisker plot of the 10 Great Value cookies, and we see here that there are no outliers because the box and whisker plot would show outliers, and we know that especially the Great Value one, they're not spectacularly skewed. Notice that the two 25% and 75% bars are about the same, so it's pretty close. And then down here are two little dot plots of the data. And notice that, again, there's no strong outliers. This one's a little bit far away, but it's not, an outlier would be out here, right? They're not really highly skewed. This one looks not exactly, mounded and symmetrical, but they're not highly skewed. So we're going to go with it. The T procedures are pretty robust, meaning they'll still work pretty well even if the data is not perfect. Okay? So again, this we have to do. That bit right there, we have to do if n is less than or equal to 30 for means, if the sample size is small, and if sigma is unknown. We've got to make a little plot, a little graph of the sample data so that we can infer that since the sample data are kind of symmetrical and there are no strong outliers, we can assume that the corresponding populations are approximately normally distributed. Since the populations are approximately normally distributed, we can infer from that the sampling distribution, that the individual sampling distributions would be approximately normal as well. It's a long chain of reasoning, but we have to do that. Okay? So now it looks like our conditions 3 are fulfilled. Do for these data, X bar Chips Ahoy was 18.4, standard deviation is 1.78, X bar Great Value is 19.4, standard deviation of the sample was 3.60. How did we know that? We plunked them into our calculator and used 1var stats. Okay? That's how we did it. Now, they both had a sample size of 10, and so the degrees of freedom for both of them were the same size, is equal to 9. So degrees of freedom is equal to 9, as you see. Okay? So here is the confidence interval. 18.4 minus 19.4 is negative 1, as it happens, plus or minus, and then this 3.250 comes from the t-table, where we look up a 99% confidence interval on the t-table for degrees of freedom equal to 9. And I'm going to make a separate video of just looking that up, so that if that's the question, if you're going, oh, Mr. Waters, I don't remember how to do that, I'm going to make a separate little video showing just that piece. I don't want to make any of these videos too long. Okay, but anyway, from the table it comes out to be 3.250, right? And so here we used the same standard error formula, where that's where that's the S of the Chips Ahoy, and that's the S of the Great Value, 10 and 10 sample sizes, blue. And here is that's our point estimate. This is our margin of error, we called it, right? And that combines to give us this confidence interval here. Using technology, we used as we called it up here, the 2-sample T interval on our calculators, which I'll show also on that other video that I just talked about. Using degrees of freedom, it tells us using technology that the degrees of freedom would be 13.145. That uses another calculator formula, and it would give us that confidence interval. Since the degrees of freedom are different, either one would be correct, you understand. It's just that this one, you notice that this one that we calculated by hand is the wider confidence interval, because it's the more conservative, because we're using a smaller degrees of freedom. And if we don't have technology, that the more conservative one is the one we would use. We conclude we're 99% confident that the interval from negative 4.81 to positive 2.81 captures the true difference in the mean number of chocolate chips and Chips Ahoy and Great Values. Well, we see here that sample interval, that confidence interval, includes 0. That is no difference, right? So since 0, no difference, is one of the plausible intervals, then we could say that this sample does not give us convincing evidence that there is a difference in the mean number of chocolate chips in Chips Ahoy and Great Value chocolate chip cookies. All right, now on to the last page here. And that is the significance test. Okay? Here's what a significance test would look like. After buying many helium balloons, only to see them deflate within a couple of days, Aaron and Jenna decided to test if helium-filled balloons deflate faster than air-filled balloons. To find out, they bought 60 balloons and randomly divided them into 2 piles of 30, filling the balloons in the first pile with helium and the balloons in the second pile with air. So this is, rather than 2 random samples from 2 populations, you understand, they're doing an experiment here, right? Because they're doing something to the balloons. Okay, and they've got, that is, what they're doing is they're feeling they're making the gas that they're in the 2 balloons is the difference. They're putting one kind of gas in one and one kind of gas in the other one to compare the difference, so that there's a treatment for the 2 balloons. Okay, and then they randomly assign to 2 different treatment groups, right? So that's the same thing as 2 different random samples from 2 different populations. Okay, and so they randomly assigned them to 2 piles of 30. They filled balloons in the first pile with helium and the balloons in the second pile with air. Then they measured the circumference of each balloon immediately after being filled, and then again 3 days later, because that's what they're going to compare, you understand. The immediate circumference of the balloon and the circumference at the end. That's the number that they will use to compare the 2 populations. The average decrease in circumference of the helium-filled balloons was 26.5, with a standard deviation of 1.92, and the average decrease of the air-filled balloons was 2.1, with a standard deviation of 2.79. Okay? Do these data provide convincing evidence that the helium-filled balloons deflate faster than the air-filled balloons? Interpret the p-value that you got in the context of this study. So, again, to make this faster, I'm going to go straight here, okay? You want to perform a test of the null of mu helium minus mu air equals 0. That is, in other words, if there's no difference, there's nothing going on, it shouldn't make any difference at all whether it's air or helium, the average difference in the population should be 0. Versus Ha, well, they thought the helium, that the helium deflated faster, so that the average increase, the average difference for helium, the average decrease should be larger. That is, remember, our test statistic is going to be the mean decrease. So the helium decrease should be bigger than the air decrease. Guys get that? That's why they're using the alternate hypothesis greater than 0. And they're going to do it at the 5% significance level. It's important to make sure we understand what the parameter of interest is here. Okay, so we understand how to set the alternate hypothesis correctly. Okay, if the conditions are met, we'll do a 2-sample t-test, right? Mu helium minus mu air. Random. The data come from 2 groups in a randomized experiment, meaning that from a sample, they put some balloons in the helium group and they randomly assigned the other 30 to the air group. Okay, 10%. Not necessary because we're not sampling with replacement. So since we're in effect replacing everything, every sample is going to be different. So we don't have to worry about the 10% rule. Normal, large sample, okay, they took 30 balloons, so our sample size was 30 or greater, right? And so that was good. The large sample, the large counts rule is fulfilled. Okay, so we calculate the t statistic. Okay, so this is, remember, is the alternate minus the null, in effect. So the null is 0. So when we're comparing 2 populations, and we had the same thing with a confidence interval, So this is, it's still going to be 0. It's, in effect, x bar minus x, minus mu. And mu, but in this case, mu is mu1 minus mu2. That's the mean difference, and our null is 0. Okay? Always going to be 0 for our purposes. Okay, so this is the standard error again, and we get a t-statistic of 39.46. Okay? That's a really big T. Right? That's the number of standard deviations that if the difference is as big as the one they got, from 26.5 down to 2, right, inches of difference, that we'd get a t-statistic of 39.46. It would be 39 standard deviations away. The degrees of freedom are 30 minus 29. Again, it's the same because both sample sizes are the same. And the p-value effectively is 0. Okay, t of 39.4 is not anywhere on the t-table. If you used, on your calculator, the 2-sample t-test, the degrees of freedom turn out to be 51.4, and your calculator would get, it wouldn't say 0, it would say like 1 times 10 to the negative 52 or something. It'd be a really tiny number, effectively 0. Conclude, because the p-value of approximately 0 is less than alpha equals 0.05, we reject null. We reject the null. There is convincing evidence that the helium-filled balloons deflated faster than the air-filled balloons. Okay? So interpreting the p-value, assuming that the mean difference decrease in circumference is the same for helium-filled and for air-filled balloons, in other words, assuming that the null is true, there is approximately a 0% probability of getting a difference of 2.44 centimeters or more by chance alone. Okay, and the last example we'll do some other time. Okay, so that's quite a lot here. I'm going to do a separate video where I'm going to do calculating the p-values either on a t-table or on using the calculator. Anyway, very good.